Good afternoon, everybody. Thank you guys for being here. Welcome to our September 2025 installment of ENERCALC Office Hours. As always, we have just a few housekeeping items before we get going on the program. If you're a repeat attendee, you know the drill. If you're new here, we have just a few things to get out of the way. One of those things is to start with a sound check. So if you direct your attention to the bottom menu of the Zoom window in your browser or your desktop app, you'll see the chat tool. We also have the reaction emoji tools down there. If you're able to hear me just fine right now, go ahead and throw a thumbs up emoji in the chat. Give us an okay, give us a reaction, applause, your choice. Perfect. That's great. Thank you guys for confirming that. Before we get on to the rest of our housekeeping items, we'll also go ahead and do a sound check and a visual check for our primary speaker as well. So Mac is going to go ahead and share his screen right now. And once again, if you can hear Mac's voice and see his screen in just a moment, then go ahead and give us a thumbs up, give us a reaction, let us know that you can see and hear just fine. Go ahead, Mac.
Hi everyone, and welcome to another office hour session.
Perfect. All right. Thank you guys for helping us confirm that. Now that we have our tech checks out of the way, we are going to go ahead and disable the chat. We will still have our Q&A capability for interaction later in today's program. So let's get on to some introductions. My name is Seth Roseworm. I'm a senior structural engineer and software developer here at ENERCALC. Our presenter for the monthly ENERCALC Office Hours program is Mac Elterhony. A lot of you guys know Mac by now. He's been doing this for a while. He's also been an ENERCALC user for a while. Max is a senior structural engineer here at ENERCALC, and he kind of splits his time between providing technical training for ENERCALC customers, working with the ENERCALC engineering team on specifications, technical behavior of the software, and then helping maintain a presence for ENERCALC at national and regional events throughout the structural engineering industry. And a lot of you also know Mac professionally because he's the founder and managing principal of Elta Design Group, which is a specialty structural engineering firm, and he's been an ENERCALC user for about a decade, so he has a lot of great insight about the needs of our customers and daily workflows for ENERCALC users. For anybody who's new here this month, Office Hours program is a monthly recurring webinar that we put on every month, free and open to the public, meant to provide direct communication between us and our users, and we do that mainly through showcasing new features and updates in ENERCALC, letting you guys know what the development team and engineering team have rolled out from month to month, showing deep dive optimized workflows on specific modules, and then live Q&A. Deep testing and research that's going to be a better fit for going directly to our support team because they can look under the hood and get you better answers. Um, as a minor point of order, you will notice that everybody's microphones are muted just to make sure we don't get any echo or feedback while Mac is presenting. And as I mentioned, we do always have open Q&A at the end of every session. If you want to submit a question for today's Q&A, use the Q&A chat, or excuse me, the Q&A dialog in the lower dashboard of your window. If you ever experience any audio problems at any point during the session, you should be able to simply refresh your browser or close out of the session and rejoin. And if you ever want to rewatch today's Office Hours program or you want to share today's program with someone else on your team, those recordings are all posted to the Office Hours playlist on ENERCALC's YouTube channel, which you can also access through our website on the Office Hours page. With that, I will go ahead and hand it over to Mac to get going on our great program for today.
All right. Hello, everyone, and thank you, Seth, for the introduction. And welcome to another session of our monthly office hours program. As Seth said, my name is Mac Eltarhouni, and I'm excited to be presenting to you today about the torsional analysis of rigid diaphragm module from the ENERCALC's library of diverse and extensive modules. So I'd like to start our session with a brief overview of the overall agenda. Today we'll be covering PDH announcement, ENERCALC latest build, what's new in ENERCALC, and of course the meat of the presentation is torsion analysis of rigid diaphragm. And then lastly, we'll talk about registration for future office hours to get notified in your email, and of course a live Q&A at the very end of the session. This session is going to be a little bit beefier than normal, so we're going to try to do our announcements a little quickly, and then we can jump directly into the main part of the presentation. So I want to begin with the PDH announcement here. So beginning with the session that we held back in May, we started offering zero point 0.5 PDH hours to the attendees to represent the guaranteed technical portion of the presentation. So the name we use in these certificates is the name that you used to enter today's Zoom meeting. So make sure you, when you enter the meeting, you just put the name that you want to be printed on the certificate. And of course, if you made a mistake or something, you can always contact us and we can correct the name for you, no problems. And you will be able to get an email with us, a separate email that has the certificate within about 10 days after the session with a link for you to download the certificate. I'd like to encourage everyone to check your software, make sure you're using the latest and greatest of ENERCALC. Because if you can take a minute here and take a look at the top portion of the software, this shows the build that you're on. We do release monthly updates and sometimes twice a month, so please take advantage of this. Because our team works hard on addressing a lot of the ongoing issues, a lot of the reported bugs, or all of these fixes. And of course, we continuously try to develop new material, update codes, and all of that. So to take advantage of the latest and greatest, you need to update to the latest and greatest. The current build as of today is 2025. 9.4, that's September 4th. So this was released 6 days ago. So to update your ENERCALC, all you have to do is just click on the update button here at the top of the program, and then this window will appear right here. So all you have to do is just click this button right here to launch for our users web page, and that will take you to our website. And all you have to do, click on download the updater file. Once you get that, you can run it, and voila, you are done. So if you'd like the program, of course, to automatically check for updates at program startup, you can check this option. And I would recommend having this option checked all the time, so it lets you know that a new update is available. And a quick note here for the users who are stuck in this range of builds. So if your build is 2023 August 30th to 2024 02 or February 28th, if you are stuck in between these builds, then the feature that notifies you of the availability of new updates does not function properly. So that means you will have to do one manual update. You'll have to go inside again, you click on the update button, and then you click on this and you update ENERCALC manually. And once you do that, then everything will be fixed and you will start getting notified in the future of all new updates. And again, the current build is 2025-09-04. Moving on, if you prefer to be notified of the latest ENERCALC updates by email, you can scan this QR code or go to enercalc.com/update-emails and just put information here, and it will let you know whenever a new update is released. So now, if you have not been using the latest and greatest build of ENERCALC, I want to just highlight a few features, and those features are important because I've been highlighting them for the past few months, but we still get people who are surprised that we support this or we support that. So that's why it's important for me to just repeat this information monthly. So I want to start with the IBC 2024 and decoupling of IBC and ASCE. So ENERCALC supports IBC 24 and all of the referenced design standards. So once you click on this button right here, the building code and load combinations, you'll be taken to this page right here that has IBC 24, 21, 18, and 15, and of course the corresponding design references. So all of that is updated, and the new thing that we have implemented recently is that we have decoupled the ASCE version from the IBC version. So you can use IBC 2018 with ASCE 2022. This is just in response to some jurisdictions requesting or requiring the engineers to produce calculations with an IBC version that doesn't match the ASCE version. A lot of times they end up adopting a newer version of the ASCE before they adopt the corresponding IBC edition. And this way, now the engineer can perform those calculations and have all of that information automatically included in the printed set without needing to do any post-processing in a PDF or something like that. Now, it's important to know that when you change the code, the IBC and the ASCE, when you change it here, again, by clicking on this button, what happens is that this changes the code selection for the project that you're working on only. This does not become your default for future projects. If you need to change the code selection for all of your future projects, using this a particular code selection as a default value, what you need to do, you need to go to the top left corner, click on settings, then click on default governing code and ASCE 7 edition, and this menu will pop up. You can choose the IBC and the ASCE editions that you would like, and you click select. This will ensure that every new project you start in the future will have this specific selection that you decided for all of your future projects. So the next update is that we have a bunch of new tabs right here that got added to the add menu, and we added a tab for seismic loads and a tab for wind loads and tab for other loads. So every time we want to add a seismic loads module or a wind load module, they will go into their respective tabs, and the other loads, this one would house the other types of loads, such as right now we have live load reduction and we have snow loads. And it's important to note that these tabs will only show up if you are using ASCE 722. So if you selected ASCE 722, these additional 3 tabs right here will show up in the menu. Now, if you are on an older version of the ASCE, ASCE 16 or 10, then ENERCALC will revert to the old menu options. And that menu option, for your reference, it looks like this. All of the seismic load and wind load and other loads, they come in preloaded right here, and you can see them. This is all the ASCE 716 and ASCE 710. All of that is right here, and of course, the other 3 tabs will disappear. So based on this selection, you can find this information in different places. ASCE 722 will give you the new tabs. ASCE 716 and older will push you to revert to the older way of displaying these modules. Native load linking with ENERCALC has been an exciting and a popular feature with rapid development. For those who don't know, load linking is an ENERCALC native feature that gives the user the ability to automatically link reactions from one calculation to another. This gives you the ability to change something in one member and have the effects of that change trickle down to all the supporting members. So load linking is currently available for steel beams, wood beams, steel columns, and wood columns, with more integrations to come. And of course, these integrations this support is two-way support. So you can take something something from a steel beam to a wood column. You can take something from steel beam to wood column, or whatever combination, maybe steel beam to wood beam. So they go kind of back and forth for maximum versatility. So if you'd like to learn more about load linking, we created a playlist of short videos on YouTube to walk you through how to use load linking step by step, so you can start leveraging this powerful tool in your daily workflow. I also added a new video recently to that YouTube load linking playlist for a full practical example of how to use load linking in real life design applications to transfer reactions from beams to columns. And this example covers both wood and steel materials. And this is the additional example is right here. Overall, load linking is a powerful tool that allows the engineers to create a well-connected chain of calculations while minimizing the risk of transcription errors. And another update we have for you is the ability to export tabular detailed results from ENERCALC to a CSV file. This is useful to many engineers who want to post-process some of the results outside of ENERCALC. All you need to do is just find the result that you want and just right-click, and this menu will appear, and you can just say save to CSV, and that will export it to CSV and download it to your computer. You can export results to CSV in all of our modules, including columns, beams, slender walls, shear walls, foundations, and analysis modules. So you can get all of the results, the incremental and intermediate results that you need for post-processing. And by popular demand, we made an important update to the general footing module. Our users now have the option to specify top reinforcement in the footing for those cases where the footing experiences tension at the top, rather than, of course, the typical case where the tension is at the bottom of the footing. You can specify the rebar size and quantity separately for each direction, top and bottom. So you can do parallel to X. You can specify parallel to X and parallel to Z at the bottom reinforcement. And then if you have a top reinforcement, you can again specify parallel to X and parallel to Z separately for maximum flexibility. And as the results get displayed here, this is a snippet from the results summary. You can see that we try to add a little bit more information here to help you navigate. So for example, ENERCALC now notifies you that, if this is top tension, bottom tension, it just gives you some good information on what's going on, so you understand, where everything is and where you need to add steel or remove steel or do whatever you need to do to optimize your size, the size of the footing. Another item we want to highlight is ENERCALC for Revit. This has been extremely popular. ENERCALC for Revit is a Revit plugin that allows you to design structural members fully within Revit without having to export information to another calculation software. You are not building an analytical model and trying to export a stick model and trying to manipulate the nodes. You're not doing any of that. This relies on your Revit model. This relies on your modeled physical geometry. This is a very simple point and click system where you click on a beam, it automatically detects the supports for it. It tells you, okay, well, what kind of load do you have here? So it walks you through the process like with a wizard type of prompts, and eventually it'll tell you to pick the size that you need. And lastly, once you pick the size, once you make sure that it's all good, you can click OK, and Revit will automatically update the size in 3D space for you. So this is a very smart, very easy to use tool, and you can do steel beams. You can do a full gravity load path because it can do beams, columns, and foundations. It does composite beams. It does wood beams. So it's extremely versatile, and there is more development to come to integrate more and more of more materials and more design capabilities. So with every new update to ENERCALC, we send release notes to outline what changed and what got updated and what got fixed. So this gives you a quick idea about the top changes that you can take advantage of, new features, and know that certain bugs have already been fixed in case that you've been having troubles with one of the issues that we addressed. So if you want to subscribe to those notes, just if you want to see what they look like, you can always just go to the, again, update button and just click subscribe to new build email updates, and this will tell you exactly what we changed in case you're trying to track a particular feature request or an update to a calculation module. So moving on, the focus of our presentation today is torsional analysis of rigid diaphragms. And rigid diaphragms are all around us. A lot of times you're designing one-story building or maybe two-story building, and you're not doing a full FEA analysis, you're not doing a full 3D modeling of the building, and you are just designing it one member at a time. So with that, a lot of times you want to perform torsion analysis on a rigid diaphragm, such as a concrete slab or something, and you have your shear walls, and you're trying to figure out how the loads are coming together. And ENERCALC here has an extremely powerful tool that recently got even more updates. So without further ado, I want to dive into this. I have an example that covers all of this, and we want to go through that. So a quick overview of the capabilities and the features of this module. It performs extensive analysis of rigid diaphragm based on various time-consuming scenarios. It takes the loads from different directions, and it does a variety of things. Second, it has diverse analysis options to accommodate the comprehensive needs of the design engineer. The user has the option to model different types of resisting elements. This includes walls, bending members, and generic resisting elements. Detailed documentations of the rigorous analysis process that ENERCALC uses to arrive to the final results is also shown in our user manual, and we'll talk about it briefly. And lastly, we have, of course, as the case with most of ENERCALC modules, you have dynamic 2D and 3D sketches for visual confirmation of the overall construction assembly, including the location of the center of rigidity and the center of mass, and all of that is shown in a dynamic fashion that allows you to perform visual confirmations. So the objective of today's session is to walk through a real-life example to demonstrate how this module can streamline your analysis process. Along the way, we will also discover the various options that ENERCALC offers that even though they don't apply to this example, we will still entertain them, look at them, and see what they do in order for everyone today form a robust understanding of this module's capabilities. So our example is clean. We have this rectangular slab. And what we have here, we have 3 shear walls, concrete shear walls, A, B, and C. They're all 8-inch thick and 12-inch tall. And then they have, different lengths. We have the center of mass location at 42.5 feet in the X direction and 20 feet in the Y direction. We need to consider 5% accidental torsion. We have a maximum force in the X direction of 23 kips, and we have a maximum force in the Y direction of 17 kips. And we want to use ASC 7 orthogonal combination procedure. And this is because the way that these walls are laid out, they're not orthogonal. to each other. So what we have to deal with, especially if you're in seismic design category C, um, this pushes you into a different section of ASCE. This is structure with non-parallel system irregularities, meaning that these walls are not orthogonal to each other. So you have to perform the analysis based on ASCE 7 orthogonal combination procedure, and we will discuss this shortly. But that's the gist of what we need to do today. So without further ado, let's dive into how to do that. So to start, this is the simple start that you have for all of our other modules. You, of course, click at the Add button here, and then you navigate to the Analysis tab, and then click on Torsion Analysis of Rigid Diaphragm. This module has two primary input tabs right here at the top. The first one is Dimensions and Loads tab. As always, we start by giving our calculation a name. In this case, I will use the acronym TAORD for torsion analysis of rigid diaphragm. Very simple, just very quick. Moving on, the next item is the location of shear application. So the shear force is applied at the center of mass, and it is important to know that ENERCALC does not calculate the location of center of mass. This is because ENERCALC does not collect floor dimension or other information, material or whatever, other information needed for us to determine the center of mass. Hence, the location of shear application is a user input. And in this case, since the floor or the slab is rectangular, the center of mass is at 85 divided by 2, which is right here. That's the x dimension, which is 42.5, and 40 divided by 2 in the y direction, which is 20. And this is from the datum. And as you can see, the datum point, the 0, 0 coordinate origin point is right here. This is for all of all analyses in this module. That's where everything starts. Next, we need to define if we want to consider any accidental torsion. In this example, we need to consider the plus or minus 5% accidental torsion, since this is an ASCE 7 requirement to account for many things. The reason that we include this is to account for, or the reason ASCE requires it, is to account for uneven distribution of live load mass during a lateral loading event, variation between computed and actual values of structural properties, all of that. So this way we have to include the 5% just to account for all of this. And in order for ENERCALC to calculate the accidental torsion, we have to provide ENERCALC with the maximum dimensions in the x direction and the maximum dimension in the y direction. So in this case, maximum dimension in the x is 85, maximum dimension in the y is 40. So with that, you can see here, based on the current floor plan we have in this example, accidental eccentricity in the x direction, plus or minus 5% of 85, which is 4.25, and 5% of 40 is plus or minus 2 feet in the y direction. The next topic is loading. So ENERCALC allows you to apply the loading in 3 different ways. So loading can be applied by picking one of these 3 options. Starting with the first option, the first method is to specify concurrent, primary, and orthogonal forces. So concurrent, primary, and orthogonal forces. The primary lateral force is the primary force to be applied to the rigid diaphragm. This is the first part right here, primary lateral force. And then the additional orthogonal force is an optional force that is applied at a 90-degree angle to the primary lateral force. So you have the primary lateral force that's applied in one direction, and then you can, and this is optional, you don't have to put anything, but if you do, that is considered orthogonal to the first force that you, or the primary force that you applied. ENERCALC calculates the resultant load, which is calculated as the square root of the sum of the squares of the primary and the orthogonal force. And this value that we use for the resultant load will be applied as directed by the user. So we have apply a lateral load that's primary, and then we have an orthogonal, then we come up with a resultant, and then to apply that resultant in a particular direction, we can visit that in the next couple of slides. We will tell them we have the ability to control the exact direction we want that force applied at. But for now, if you put these two loads, they will get added together and calculated, or the resultant will be calculated from these two loads. So that is option number one for you. If that is not how you want to apply the load, you can apply it following method number two. And this method is to specify X and Y forces resolved by load angle. So when this option is selected, the forces are treated as independent magnitudes. The user is asked to input the maximum lateral load in the X direction. So this force is applied at 0 or 180 degrees, so positive and negative, but that's just horizontal X. And next, it asks you to input the maximum lateral force in the Y direction. That is 90 degrees and 270 degrees. Once both of these loads are determined, once we apply them, then they can be used for analysis of the diaphragm. So for example, if the loads are applied at 30 degrees, then the force is really split into maximum fx times cosine 30, and it's added to maximum fy sine 30. So this is the total shear that is applied to the diaphragm. So you're putting two independent forces, and based on the load angle application, that's what we use to grab the component from the X direction and the component from the Y direction that goes into the applied, 30 degrees or 70 degrees or whatever. So that's pretty much how this one works. And again, all of these are useful in different scenarios. And keep in mind for us to have a comprehensive understanding of the most critical case, you want to apply the loads at different angles. So maybe you start applying the load at 0, and then maybe at 30, and then at 60, and then at 90. So the load gets applied and rotated around the diaphragm, so you can see which load or which angle or which direction results in the maximum the maximum shear load or maximum load per resisting element, which is, determining the most critical cases per resisting element. The third method, and this is the meat of today's presentation, or the focus of today's presentation, this is the ASCE7 orthogonal combination method. So this method uses the prescribed ASCE7 procedure. The diaphragm performed, the module will perform a comprehensive analysis by pretty much performing a series of analyses where it loads the diaphragm simultaneously with 100% of lateral force in one direction and 30% of lateral force in the perpendicular direction. The user will have to input the maximum lateral force in the X and the maximum lateral force in the y. And that's what our example is asking, is saying that we have a maximum force in the x of 23 and a maximum force in the y of 17. And now we need to combine them based on the ASCE methodology, ASCE7 methodology, to examine this diaphragm and determine the load that's going into each resisting element. So to show you what ENERCALC does with the forces when you pick this option, you can see the various mutations of the forces here on the left. You start with what positive 100% in the x and positive 30 in the y. Then you do positive 100 in the x, minus 30 in the y. Then now you do minus 100 in the x, plus 30 in the y, minus 100 in the x, minus 30 in the y. That's the first four. Then you flip it. Now the 30% is on the x, while the 100% is on the y. And then you have positive and negative for each case. So you end up with a total of 8 different rigid diaphragm analyses that each will produce, different loads on the walls, and then ENERCALC will report the maximum load or the maximum shear load that's going into each resisting element, and it will tell you which case controls. So that's exactly what the ASCE7 orthogonal procedure really is all about. So moving on here, so based on our example, the maximum applied load, again, in the x direction is 23, and in the y direction is 17. And because we are using the ASCE method, we're going to have to see 8 different mutations, aka 8 different analyses. If you were doing this by hand, you will examine all of these 8 separately. So the next item in here is the load direction. This is what I was talking about earlier. We have the load, and now we need to tell it how, or tell ENERCALC how we want that load applied. So this gives the user a significant level of flexibility of running a series of analyses where the load is applied at various directions to determine the most critical case. Now, for the ASCE7 orthogonal method, the load direction controls right here, they're all disabled, and that's because ASCE already told you what you need to do, the directions. You're doing this positive and this negative, then this negative and this positive, so it's telling you exactly the various cases that you need to examine. So you no longer have the need to tell it, to give information on the direction of the load. This knows exactly the various cases that it needs to create. However, if you are using one of the 2 methods that I specified earlier, that I was talking about earlier, the other 2 options, then the load direction options will be enabled so you can make a selection. The user can analyze the load in many directions or analyze the load in one specific direction. So option number 1, you can do it in many directions. Option number 2, you do it in a one specific direction. You have a very specific case that you want to look at. So I'm going to start with option number 2 because that's the easier one to explain. So I'm going to start with this. So loading in a specific direction, you can select to only check the positive and negative x directions. That means all you want to check is just the x direction. That means the 0, which is positive x, and 180, which is negative x. That's all you want to check. Or you can pick this one right here, and this will only check positive y and negative y, 90 and 270. Now, a third option would be is to specify, and that is to specify the angle where you want the load to be acting. So if it's not 0 or 180, and if it's not 90 and 270, maybe you have 60 degrees or 180 or 130, 135, whatever it is. It's worth noting here that this angle is measured from the positive x-axis. So the positive, which points, to the right, that's the 0. And if you're doing the 135, then you pass the 90, and then you go all the way to 135. So you are pointing to the top left corner. So that's how to apply the load in a very specific direction, and that's exactly what ENERCALC is going to do. Now that we discussed this, let's look into applying the loads in many directions. So to apply the loads in many directions, what ENERCALC does is that it creates a series of calculations where it takes the load that you applied, whatever load you applied here, and apply it at different angles to determine the most critical case. The user can apply the load at different direction increments. That's what this is all about right here. If you want to apply positive x, negative x, positive y, negative y, aka trying to create just orthogonal plus or minus x plus or minus y, then you can say I want this I want ENERCALC to analyze the load based on 90-degree increments. So that means 0, 90, 270, and 0, 90, 180, and 270. That's if you used 90 degrees. However, the user has the ability to pick smaller increments. You can pick 15-degree increment or 30-degree increment, or you can go as low as 1-degree increment. Just know that every increment means that it's a calculation. So for example, if we did the 90-degree increments, that means we have to have, ENERCALC is going to perform 4 separate analyses to examine to come up with the most critical case. If you do 45, then now you have 8 analyses. If you do 1 degree, then it's examining 360 cases to come up with the worst case scenario. Now this is, of course, most of the time, every 1 degree is an overkill and is not needed, but you do have the option to examine this in every direction possible. So then in the summary, ENERCALC will display the maximum load per resisting element. So once it creates the 40, 50, 60, 100 analyses, it will just envelope them and give you the largest or the most critical largest load per resisting element. Now, this is such a comprehensive analysis that would take a significant amount of time and effort to do this by hand. And even if you have a spreadsheet, then your spreadsheet is doing this calculation one at a time. So you're going to have, like, I don't know, 40 different copies of your spreadsheet to check out every case, to evaluate every case. But here in ENERCALC, you can do all of this under one calculation. So you can perform this analysis again in increment of as small as 1 or as large as 90, or you can specify if you want to do this at increment of 25 degrees or something that's not standard. So moving on to the next part of this to give you a little bit more. So back to our example with ASC7 orthogonal method, this again is already specified by the orthogonal procedure, and you don't need to worry about the load direction. And then here, now that we know how the load is applied, this is just for load direction, then now we apply a similar approach to the eccentricity increments. You can evaluate eccentricity because we have accidental torsion here and 5% of maximum eccentricity. So you can evaluate the eccentricity in the positive and negative x and positive and negative y. That means you apply the load. Let's say we have a maximum eccentricity. For example, right here, this is a quick example. If you have maximum accidental eccentricity of 5 feet and maximum accidental eccentricity in the y direction of 2.5 feet, then the first case you're evaluating is 5 in the x, 0 in the y. That's pretty much 0 degrees. That's positive x. Then you look at the positive y case, which is the positive maximum accidental y eccentricity, 0x, and then 2.5 in the y. And then now you do the minus maximum accidental x eccentricity, minus 5 and 0, and then finally you get back to the bottom with the minus y, which is 0 and minus 2.5. So that's just the 4 locations that you're examining. Now, alternatively, if you really want to be even more thorough, and actually before I get into that, you can see right here that says step size is 90 degrees. Again, because positive x is 0, negative x is 180, positive y is 90, and negative y is 270. So it's almost like going from 0 to, you're just going into in 90-degree increments. Alternatively, what you can do for a more robust analysis, you can pick this option, which is evaluate incremental eccentricity. So to evaluate incremental eccentricities, you can say, I don't want the step to be 90 degrees. I want the step to be 45 degrees. So then each load will be evaluated at these eccentricities. You can see here the highlighted in yellow cases. Those are the same as the ones up here because this is the 0, then the 90, then the 180, and then the 270. However, we introduced now an intermediate step, 45, 135, 225, and 315. So now you have a different point along the eccentricity ellipse that would give you that will give you an additional load case to examine. Again, a lot of times, just the positive and negative x and y eccentricities is enough. But in case you're worried and you want to do something more robust, you can click on this option here and specify a step size that is smaller than 90 degrees. Maybe you want to do 45 or 30 or 15 even if you would like, whatever you would like to use there. As far as the ASCE 7 methodology, the orthogonal procedure methodology, all you need is the positive and negative x and y, which translates to the step size of 90 degrees right here. Now, it's important to know that if you have a smaller step, that might slow down the recalc time, especially if you go to something crazy like you want to do it, you want a step size of 1 degree and you want to apply the load in many directions at 1 degree increments. You can see here you're going to create a significant amount of analyses. So that might just slow down the process a little bit of recalculation time, but it's ENERCALC performs this immaculately. So overall, the load direction settings controls the direction of the applied lateral force, while the eccentricity increment controls the position of the force around the eccentricity ellipse. So that's an important distinction there. So let me give you here an example, again, to make sure you understand how all of this works. So if we have a load direction that is specified at 30 degrees, so if we have, let's say, 10 kips, and we want to rotate it around the diaphragm 30 degrees, or in every 30-degree increments, that's what it is. And then each load needs to have an eccentricity increment of 15 degrees. That's the step right here. So it's not just getting evaluated in 4 direction, which is plus or minus x, plus or minus y, but we want it to rotate. So the program evaluates pretty much the load direction. We have 12 cases, and then each case is applied at 24 different eccentricity positions. So this gives you 288 total rigid diaphragm analyses of force distributions to the resisting elements. And then, of course, ENERCALC will tell you the largest force per resisting element. So to take this down, my force is applied at 0 degrees. So that means it's horizontal. That's case 1. Case 1 needs to have an eccentricity of 0 degree. That means it's going to be at positive x and 0 y. Remember, this one right here. If it's 0 here, then you get all positive x and then 0 on the y. And then at 45, you kind of change the eccentricity location as you go based on this step. So in this case, because we wanted 45 degrees, then we ended up with 8 cases. 1, 2, 3, 4, 5, 6, 7, 8. But now because this step is not 45 degrees, this step is actually 15 degrees. So we end up with 24 cases. So this is the same load, the one that's pointing towards the positive x direction, is applied at the first step, which is 0 degree eccentricity, and then the second part, 15 degree, and then the third part, which is another step all the way to 30. You do this all the way until you reach 345. That is 24 cases for just the load that's applied at 0 degrees. Then now we apply the load at 30 degrees because that's what the load direction is at 30 degrees, and then move it around the eccentricity of the first one at 0, and then another step at 15, another step at 30, and so forth. You repeat this. This is the breakdown of how the cases work and how you end up at the end of this amounting 288 rigid diaphragm analyses. I'd never do this by hand. Obviously, I'll just if I'm doing this, I'd be lucky if I ended up doing 3 or 4 cases to examine this and call it good. But now that you have this powerful tool, you can do this in the blink of an eye, and you can get very accurate analysis that can help you sleep a little better at night, knowing that you left no stone unturned. So now that we fully understand the vast level of flexibility and comprehensiveness of ENERCALC analysis, we're ready to move forward with our example. We will be using ASCE 7, again, orthogonal method for loading direction, and we will only evaluate the plus and minus x and y eccentricity. This means that we have 8 load cases to cover the ASCE 7 method, which is these, but those are just load direction. And because each load direction or each load needs to be applied at positive x, minus x, positive y, and negative y, so each case out of these 8 cases, each case has 4 different eccentricity locations around around the diaphragm that it gets applied. So you end up with 32 analyses to ensure all of the bases and combinations are covered and you're in compliance with the ASCE methodology. And now that we've set up all of our loading and the analysis procedure, because pretty much we finished everything we need to do here. So we wrapped all this up. We are ready to model the resisting elements, because so far we have not modeled those resisting elements. ENERCALC allows you to model 3 types of resisting elements. The first type, most common, which is walls. The second type, bending members, and generic resisting members. For concrete and masonry shear walls, these can be modeled as walls under the wall tap. If you have column moment frames or cantilevered columns, you can model that under bending members. And lastly, generic resisting elements. This is a catch-all term that pretty much this can be used to model other resisting elements, such as braced frames or other complex resisting elements where the stiffness was determined from another analysis. So additional information, of course, will be needed here. But yeah, one of the main information that you would need to input there is the flexibility, which is the inch per kip of applied load, so ENERCALC can perform the calculations properly. So our example here has concrete walls, as we discussed. So we will model these under the walls tab. So let's start by modeling wall A. First, you click on the add button here to create a new wall element. And after that, you start inputting a lot of this information that you need. So the center of the wall location, which is 77.5 and 30, that is the center of wall. And then we have the wall orientation. This is this angle right here. Everything is done from the positive x. So this right here is 126 degrees. And then the height is 12, the length is 25 feet, and the thickness is 8 inches. Next, we have to input the bending EB and the shear EV values. So for bending, this is concrete, so we just use the modulusicity of concrete, 5,700 square root of F prime C. That ends up being 3.6 times 10 to the 6. We already have 10 to the 6 already there, so you just put 3.6. As far as the shear modulus for concrete and cementitious materials, this is a little bit trickier. I'm sure there are all kinds of conversations among concrete gurus about how to come up with a good estimate of EV. However, for cementitious materials, EV is often estimated as 0.4 times EB. And the ACI doesn't formally define EV, but it in the commentary, it presents this 0.4 value as a reasonable approximation. And the same thing, the TMS 402 shows that to be the same case for CMU. So we'll use that right here. And then this portion, that's the the fixity of the wall. So we're assuming it's fixed at the top, fixed at the bottom, and that gives you, or that tells us to use this equation right here to determine the flexibility of the wall as inch per kip. As you can see here, the flexibility in the weak axis is grayed out. This is because I enabled this option that says consider all weak axes, all weak axis wall stiffnesses to be negligible. I don't want the weak axis of the wall to be taking any load, so I'm just assuming that it's infinitely flexible, hence it won't take any load. Pretty much we do the same thing for wall B and wall C. You just put all of the information, the center, the orientation of wall B is 0 because it's parallel to the X. Orientation of wall C is 90 because it's parallel to the Y direction. And once you populate all this information, we're ready to evaluate the results. If you click on the 2D tab, you get this dynamic sketch. It shows wall A, wall B, and wall C. The green dot right here, this is the center of the load application, which is the center of mass. And you can see that the red dot right here is the center of rigidity. And this circle, that is the eccentricity. If you're going all the way to the right, that's positive X. Eccentricity here, positive Y, minus Y, and minus X. And if you have an increment of not 90 degrees, but 15 degrees or whatever, then you are somewhere along the eccentricity ellipse right here. Next, of course, we have the 3D tab, and this is always satisfying to see the modeling in 3D space because it's great, especially as a teaching tool to younger engineers to help them visualize what we're dealing with, especially that it shows already the center of rigidity and center of mass. So now that we got everything taken care of, we can click on the calculations and the summary maximums. We have A, B, and C. Those are the walls. And you can see those are global X and Y direction. That means it's global X right here and global Y right here. However, what we're interested in quickly here is the local Y direction. So the local Y of every element, the local Y is parallel to the length and the local X is parallel to the thickness. So that's why the local Y is the direction where the strong axis, where the load really is. So for wall A, we have 11.6 kips, wall B is 21.5, and wall C is 11.8. And you can see Vx is 0 because, again, we told it to ignore the stiffness, so don't give it any load. If you also check here under the all forces results, if you want to see some intermediate values, you can see that for A, look at that. Those are the 32 combinations, and you can see combination number 1, that's the eccentricity, combination number 2, that's the eccentricity, and so forth. And you can see that these two combinations are the ones that controlled, so positive 30 Fx minus 100 Fy, and at eccentricity of positive X. Same thing right here. So those are the ones that controlled for wall A. And again, those values are the same as what's being reported here. And if you go to the resisting elements, you can see again in the local x-axis, we neglected the stiffness, and that's why it says neglect. If we told it to calculate the stiffness, it would have calculated it as shown here. But you can see this one is to the along the y, the strong direction is to the power of 4, and this one is to the power of 2. So it's a lot smaller. You have a wide variety of information here that covers a lot of intermediate values, the element matrix values. It shows you the center of rigidity, the diaphragm matrix values, and the diaphragm displacement, delta X and delta Y. And it's important to know here that ENERCALC has a fully detailed theoretical information here on how this module works, so you can check it out if you want to dig deeper into this. And if you want to access this page that has all of the equations and the documentation, all you need to do is go to the calculation details and then click either on center of rigidity or the diaphragm matrix, and then click on this icon, question mark icon right here, and this will take you to the page that has all of that information. So, as always, I want to wrap this up with just saying that if you are trying to just get the maximum values, then pretty much you can do that very early on, right here from the very beginning, and get the load that's going to your wall. Otherwise, everything else is just intermediate values that you probably wouldn't need unless you're trying to dig deeper into the calculation. And again, I just want to remind everyone that it's a great idea to go to enercalc.com/office hours webpage to register for office hours, and also watch or take a look at all of the previously recorded sessions in case you missed anything, or if you want to watch this session again, it'll be uploaded right here probably within a week or so. And just to let all of our users know that we are improving our efforts to be more available to have FaceTime with our users. So we just came back from the SEOC conference, and next week I personally will be at the SEA of North Carolina annual conference. My colleague Seth will be in Columbus for the SEA of Ohio conference, and my colleagues Derek and Chelsea will be at the Northwestern Conference States Conference towards the end of the month. So if you live anywhere near these conferences, please come and say hi to us, and would like to hear your thoughts about our software and about how we can improve. So with that said, I know this took a little bit longer. This was a beefy session, but with that said, we are ready for Q&A.
All right, let's dive into some Q&A. So I just want to briefly mention, we had a couple of questions early on in the session about updating and about IBC 2021. So just wanted to remind everyone, like Max said, there's a couple different ways to update from directly inside the application and also from our website. So if you're having trouble updating, you can always go to enercalc.com under For Our Users to download the latest, greatest. And that also opens up your capability for IBC 2024 if you have a version that predates that release. So feel free to check out those answers that were written in the Q&A and reach out to support if you have any other questions. So let's get into topical technical questions for today. Is there a specific location within the ENERCALC output where the displacements and torsional moments related to the torsional analysis of a rigid diaphragm can be found? So hopefully that was mostly covered, but if Mac wants to pull up the interface, we can dive back into some of that. Obviously, the first and foremost result that's displayed is the force distribution. And then if you dive into the calculation details, like Mac was showing closer to the end of our session, you can look at granular breakdowns of how these things are calculated. So you can dive into the displacements of the diaphragm, which is your delta X, your delta Y, your delta theta, which is the torsional displacement. and then you also have the sum of k values and so on. Go ahead, Mac.
Yeah, no, that's exactly. You just go right here to the calculations detail, and you can see all of the intermediate values right here for every load case or loading condition.
All right, next question. For wall member elastic module, if we use, I assume elastic modulus, if we use wood or steel material in that case, we don't have a selection table. We need to enter the values manually, right? So this has to do with those three different options for applying resistance to your diaphragm. You have your bending, or excuse me, your wall elements, your bending resisting elements, and your generic resisting elements. So for walls and bending, you're able to put in geometry and material properties and get calculated flexibility values, which then feed into your calculation. If you don't have something that fits neatly within those categories, for example, cantilever column for bending resistance or simple planar behavior of a wall like a solid concrete shear wall or masonry shear wall, if you don't have one of those conditions, then it's more appropriate to go to that generic resisting tab where you can manually input a calculated flexibility value. For example, if you're doing an NDS wood shear wall, you would calculate the deflection of that shear wall under unit load, for example, a 1 kip lateral load, according to the NDS procedure for shear wall deflection. Then you'd be able to feed that flexibility value in as a generic resisting element. Hopefully that answers that question. Feel free to ask a follow-up.
Yeah, and just to show them, I think you guys can see on my screen, that's where I would model that right here. So generic resisting element, because under wall, it automatically calculates the flexibility just based on this equation right here. And since this equation might not be applicable, then you can just do your own calculation outside and figure out what your flexibility is, and then you can put that information right here, and then ENERCALC uses that.
All right, question from Bill. This was a good example of complex geometric wall layout, not a very good example to use for engineers learning torsional analysis of rigid diaphragms. Would you consider posting a YouTube video showing an orthogonal wall layout, maybe matching the analysis used by Omrime in the Reinforced Masonry Engineering Handbook? Good question. So, a couple things to note about this. Under orthogonal conditions, the results that you're seeing from here in ENERCALC would converge with some conventional hand analysis methods where the ENERCALC approach outpaces hand approximations is when you get into skewed elements. So we were intentionally using skewed elements here in order to show that ENERCALC supports that capability. Obviously, if you were trying to use this as a teaching exercise to teach young engineers who are not familiar with rigid diaphragm, then this would be kind of jumping into the deep end. But for if you're learning a hand analysis or you're mentoring young engineers who are learning a hand analysis, you would be able to demonstrate close convergence between the ENERCALC results and hand approximations for orthogonal conditions. Now, because this is driven by a stiffness matrix analysis that's fairly rigorous, some of those hand approximations may diverge when you get into the skewed conditions. But yes, you're correct. This was designed for experienced. Today's session in particular was designed for experienced engineers who already have a frame of reference for rigid diaphragm, and this was just mainly about how to use the tool. But once you're familiar with rigid diaphragm, you're familiar with the module. It can also be a teaching aid for young engineers as well, for sure. Mac, did you want to add to that?
Yeah, no, I agree with what you said, and I wanna emphasize that what today's session is about is that it shows you what each option does, and again, having a skewed wall, that's when this becomes powerful, because just having regular orthogonal walls, you wouldn't even need to be in the ASC 7 orthogonal combination, because you wouldn't have the irregularity anymore that I was talking about, the non-parallel regularity issue. So yeah, this was meant for someone who knows a little bit about rigid diaphragms, but to showcase that this can do a lot more, and then you can build a model that has all kinds of walls, all kinds of crazy things. and this will still handle it very efficiently.
All right. Next question from Michael. Can you please show us a real world model of the structure that you just analyzed? So, kind of like we touched on a moment ago, this was a deliberately selected model to kind of get in the sweet spot between not too complicated for a 1 hour session and not too simple as to be trivial. So, not every building we realize is going to have three resisting elements, two orthogonal and one skewed. Um, we were just trying to, in this case, do a case study that fits reasonably in the time allotted. There's a question lower down about maximum number of resisting elements. Obviously, as Mac is showing here on screen, you have the ability to go up into much more complicated analysis. This is a complicated analysis that involves generic elements in both directions, wall elements in both directions, skewed elements with a subtle skew because the building turns a corner. This could be a parking structure. This could be an L-shaped concrete frame building with shear walls and moment frames. You have the ability to go much, much more complicated with very real world, large scale commercial lateral resisting
Correct.
systems
Yeah,
for sure.
and I want to add to that is that the while it's a while the example is simplified, so you can keep the ball rolling, um, having just simple orthogonal walls that happens in real life all the time, and then having a skewed wall happens, of course, in real life all the time. But to make the example, to make things just easier, for a presentation perspective, you kind of have to water it down a little bit, but that doesn't take away from its 100% real applications. And you can see the ENERCALC can handle something like this. That's the point. That wouldn't be an example that we can cover in 30-40 minutes, but it is definitely, you can see here your skewed wall right here, orthogonal walls, everything is, you have different type of resisting elements. So the idea here is that what we did today can be amplified to model something that is quite complex and be very useful in your daily applications. But this doesn't require any additional knowledge than what we covered today. It's just more of it, that's all.
All right. Next question. How do you consider diaphragm opening? So, just to be totally clear on what we're discussing today, we're talking about analysis of a diaphragm, specifically relating to distribution of forces from the diaphragm onto the resisting elements. What we're not looking at today and what we're not looking at in this particular module is the actual capacity of the diaphragm or the detailing of the diaphragm to ensure that the diaphragm actually has truly rigid behavior. So the torsional analysis of rigid diaphragm module pre assumes that we have rigid floor behavior, which is capable of distributing force in that manner. It would be outside the scope of that module to verify through detailing and other design that your floor does meet those requirements. And Mac, go ahead. I
And
see you're highlighting some
yeah,
documentation there.
I do recommend that every time you're working with any ENERCALC module to just click on this little question mark thing, because that will take you to the exact page in the user manual. So for the torsion analysis of rigid diaphragm, the first thing we list the limitations, and the first thing is that it does assume that rigid diaphragm, flexible diaphragm effects are not included, and it assumes that it's already rigid and it's been detailed properly for that. But I just wanted to highlight the user manual here, because there's so much information. A lot of the snippets that I brought today actually into the presentation are from the user manual. The user manual is packed with really useful information. So um, I encourage everyone to take a look at it and see how how our flexibilities are calculated and where they come from, the shape factor, everything that we include here is just useful material in my opinion, to get people moving in the right direction.
Yeah, and I just want to chime in while Mac is showing the documentation there. If we dive a little deeper in the rigid diaphragm theory, um, to kind of call back to Bill's question earlier about young engineers who are just learning about rigid diaphragm, a lot of the new documentation that Derek and the rest of the engineering team have helped curate in here for the rigid diaphragm theory section can be extremely instructive for young engineers who are just getting into the concept of what is a rigid diaphragm, how is this behaving structurally, what is the actual engineering math behind how the system is being characterized, how the forces are being distributed. You can basically walk through using this documentation and the granular outputs that Mac was showing you guys, and you'll be able to demonstrate convergence to the penny between hand calculation and what's being shown in the module and get an understanding of the theory from a very fundamental standpoint. So that's some really great resources as far as the mentoring of young engineers.
Yeah, absolutely. And we're working on creating here a little bit more documentation, but you can really follow this quite a bit, and you can see a lot of the intermediate values that I was talking about earlier. If you click on calculations detail, and for example, center of rigidity, you can see all of that information, how it's pulled together and how it eventually calculates, the location of it, X and Y. All of this information, the summation of kx, summation of kxx, and all of that, it's exactly coming to play right here and going into the calculation here. So anyone can perform a hand calculation following the methodology here to converge exactly with the results that ENERCALC shows.
Absolutely. All right, next question. Does ENERCALC have any plans to add load linking from the rigid diaphragm analysis to concrete or masonry analysis modules in ENERCALC? There absolutely would be that capability for possible future work. If you want to make a feature request, you can definitely reach out to support@enercalc.com to dip your oar in the water on feature requests for future development efforts. And then it's also worth noting if you're interacting with a module that does have load linking capabilities already exposed, there's a couple places where you can actually go in and vote in a survey about what load linking capabilities do you want to see incorporated next in ENERCALC. I don't recall off the top of my head if the lateral modules or rigid diaphragm are included explicitly on that survey. Um, but you can at least take a look and see what those options are to make your voice heard about what load linking features you want to see in the future, and definitely send that over to the engineering team at support@enercalc.com as well. All right, next question. We frequently have buildings with more shear resisting elements than your current maximum. Can you look into adding more? So, just to make sure we're on the same page about that, the current maximum, I believe, is 160 resisting elements, which is a pretty decent number. But if you find that you're consistently bumping up against that limit and it's still is not meeting your needs, definitely reach out to the support team, and we can look at your situation and look at how many other customers, if any, are asking about that to see if that warrants attention from the development team. So definitely reach out to the support team about that. We'll want to hear more about what you have going on.
Yeah, and yeah, it's right there. So yeah, it supports up to 160 different resisting elements. I'm not sure if he said the number or not, but
Mm-hmm.
yeah.
That's perfect. All right, next question. How can I print out displacements and torsional moments results in PDF? I do not see those results in the summary. So one thing I will note is to to make sure that you have the latest, greatest build, because torsional analysis of rigid diaphragm, the reason that it's being talked about today is it recently went through a lot of fantastic changes where we improved all the granularity of those outputs that Mac was showing you. We improved a lot of the wayfinding and navigation on the input side, introduced all those new granular results tables. Not everything that you guys saw today in those tables on the output side are being incorporated directly into the report. Some of them are, some of them are not, just because of the large amount of analysis results. Not all those are exhaustively included in the report. So if that's something where you have something that you specifically need to see in the printed report or would like to see in the printed report, feel free to reach out to the support team with a feature request, and we'll see what we can figure out on that. But in the meantime, you do at least have all of those results in tremendous detail in the output side of the application itself. All right. Well, we're about one. Oh, I see another question coming in here. Oh, that was just a thank you. Good job, Mac.
Yeah. Well, thank you for being
Um,
here.
I think we're about 20 minutes after the hour. That was a lot of ground to cover, so we appreciate everybody sticking with us and all the great questions and discussion. Mac, do you want to close us out with a teaser for next month?
Well, the topic is still to be determined. We haven't decided which topic we're doing next month, but our next session is going to be October 8th. So come ready and come with your questions, and we'll see you then.
All right, good deal. Well, as always, we thank everybody for your time and attention today. It's always great to connect with you guys. Thank you for coming with your questions, your participation, and everything. Like Max said, bring your questions for next month. Don't hesitate to reach out to the support team at any time with any questions you guys have. And we'll look forward to seeing everybody next month. Thank you all and have a good one.